Modern PC games require a lot of processing power, so game developers are always looking for more ways to squeeze extra power out of current hardware. One way to do that is to split up the workload of the game's logic and graphics among the cores of a CPU in a process known as multithreading. But this isn't as easy to implement as it sounds, and you'll often find that multithreading doesn't provide huge gains in frame rates like you would expect. So why does this happen? We're going to answer that in this video on how multithreading works. When you have a single thread of logic running, it seems intuitive to double its performance by just splitting the work of that thread into two separate threads. So let's say we have a simple program that just updates something we'll call thread output with the number 1. In this case, it does it 50 times and writes it to the screen like this. This process takes 785 milliseconds to finish doing its thing. Now I want to take advantage of the extra cores in my CPU to make this program go faster. So I create an updated program that has two identical display threads that will work together to do the same job. Thread 1 will write a 1 to thread output, and thread 2 will write a 2. Each time one of them writes a line, it'll look like this. So when thread 1 writes to the screen, we should see thread 1 output, followed by an arrow and the number 1. And down here, we should see thread 2 output with an arrow and a number 2. Simple enough, right? But that's not what we end up seeing. Instead, we get this. A lot of these lines show what we expect, but every now and then we see these mismatch lines where a 2 shows up in thread 1's output or a 1 in 2's output. What's going on here is that both threads are rushing to get done with their tasks as fast as possible and then push their result into thread output. Since thread output is shared among both threads, it's possible that they can overwrite each other's work. Without some form of external control to act like a traffic cop, they end up racing each other to see who can push an update first. This is known as a race condition, and it's one of the dangers of multithreading development. What we need to solve this problem is a traffic cop. This traffic cop would stop the other thread from interfering with the shared data and thread output until the first thread is done with it. This functionality is known as a thread lock, and it looks like this in code. Each one of our two threads here has a lock that keeps out other threads until it's done with its task. So when we run it with thread locking, we see that now all the lines match up. Thread 1 no longer has 2's output, but now we've run into another problem. Look at the elapsed time. When we did this with the single thread, it was 785 milliseconds. Now it's 773. That isn't much of an improvement. So what went wrong? Nothing's actually wrong here. It's just that a thread that's been told to stop and wait is going to do exactly that. It's not working while it's waiting in line to update the shared resource. So in the end, we didn't really save much time. Even when we split it up among 10 threads, we only get down to 767 milliseconds. Does that mean that multithreading is pointless? Not at all. Our bottleneck is the shared resource. So our threads are wasting time idling while they wait for it to be freed up. The solution here is to split that shared resource up into two parts. Now thread locking is no longer a problem, but this introduces a new challenge. These two resources are no longer related. As they get updated, they are completely unsynchronized. But that's okay. This is a multi-threaded app, so we can just spin up a new thread to synchronize them. All this synchronization thread will do is add up the values from the two separate resources. Once they reach a point where they are ready to be combined, the synchronization thread will display the total on the screen along with the elapsed time. Here's what that looks like. We can see our two threads steadily working through their jobs. Since they're using separate resources for their output, we don't see any race conditions corrupting our output. Down here, we see the threads took about 400 milliseconds to complete their tasks. So altogether, it's about half the time of a single thread doing the same thing. But we needed a little more time for the synchronization thread to give us the final result. In this case, it was about an extra 30 milliseconds. Synchronization isn't free. It adds a little extra overhead in our very simple example. A complex game like DCS isn't going to be as easy to divide up into manageable threads, so the synchronization is going to take up a lot more overhead. Since a lot of my viewers are into DCS, I thought I would share my thoughts on the upcoming multi-threading update to the game. The dev team announced that the game's main thread is going to be split into 2 concurrent threads, so I would expect to see a performance increase like what we just went over in this video. But that's not the only change coming to DCS. Technologies like the Vulkan API, DLSS, and a new render graph pipeline will all be adding performance to the game. But we won't know how much of an improvement each of those will bring until everything is released. So I hope you found this video informative, and thanks for watching.